There are several ways to create objects in JavaScript, but you can do it with class. JavaScript classes introduce new ideas and concepts that didn't exist before. But like everything in JavaScript, classes come with a lot of details, often overlooked, that can make it hard to fully understand what's going on. So, if you want to learn everything you need to know about classes, build the correct mental models, and beat your imposter syndrome, then you should watch this video. This is the continuation of my previous video about objects, so if you haven't seen it, watch it before this one. But if you already have a good understanding of how objects work, then you should be good to go. I've summarized all this information into a mind map that you can get by following the link in the description. Let's start by creating an empty class. To do that, you need to specify the keyword class, followed by the name of the class you want to create, and then you add curly braces. So now we have a class, but its type is function. So let's try to call it like a function. We get a type error. Class constructor, empty class cannot be invoked with that new. So it tells us that empty class is a class constructor and that it cannot be used with that new. So if you want to create an object, we need to use the keyword new. It creates a blank object and sets its prototype to an object containing a constructor property pointing to empty class. And you can see that it's a class constructor by looking at the word class in front of it. If we compare it to an object created with the function constructor, the constructor property is followed by an F, meaning that it's a function constructor. You'll see a lot of articles and videos saying that classes are syntactic sugar for function constructors, but that's not entirely true. There are a few differences, and this is one of them. To make the difference between function constructors and classes, the specification defines the internal slot is class constructor, which is a boolean indicating whether or not the function is a class constructor. If it's true, it's a class constructor. If we try to call it like a function, which is described in the specification as invoking the function's internal method call, it will throw a type error exception, just like we saw previously. But if it's false, it's a function constructor, and we can call it like a function without getting an error. For information, the specification defines functions as function objects, which contain the internal method call and construct. When we call a function like a regular function, call is used. When we use the new operator or super, construct is invoked. So empty class is a class constructor, which is a function executing code. The code executed comes from the constructor of the class. When you don't explicitly add a constructor inside the class, an empty one will be created. This constructor is equivalent to a function constructor, so you can do everything you can normally do in a function constructor. As an example, let's say we want to create bananas. We can start by defining a class called banana. Let's add a constructor. Constructors can have arguments. In this example, we want to store the length of the banana in centimeters and its mass in grams. When we create an object with the class, JavaScript enforces the use of new. If you recall my video about JavaScript objects, you know that the new operator creates a blank object, executes the constructor function, and returns the new object. When it comes to classes, the body of the constructor will be executed, which means that inside the constructor, references to the keyword this will point to the new object created. Now that we know that we can use this to refer to the newly created object, let's store the length and mass of the banana in data properties. And let's define a function property to calculate the calories of the banana. When we define a class like this, you can think that the JavaScript engine will turn it into a function and will set its internal slot is class constructor to true. It will have the same arguments as the constructor, and its body will be the body of the constructor. When we use new to create a new object, JavaScript will take this banana function and feed it to the new operator, which will return a new object. Let's try it. We successfully created a banana object, and we can see that the properties that we define using this are own properties of the object. We can access all these properties as usual. And something I should have said in my previous video, You can use the destructuring assignment syntax to unpack properties of an object. By using this syntax, you will create variables containing the values of the properties of the same name. If you want to store the values in variables with different name, you can do so by using the following syntax. We define a function property to compute the calories of a banana, but we can also define methods which are functions associated with a class. Let's define a simple method called semi-name that will print banana. Let's create a new object with this new class. And we can call the method like a function property. The class syntax allows us to easily define accessor properties by using the keyword get and set. For example, we can set the price of bananas by specifying an index that could be the result of a computation containing information about the season, the location, and the market. And then get the price of a banana knowing this index. Now, if we try to look what the object b3 looks like, we see that it has a new property underscore price index, which was created by the setter. But we don't see the setter, getter, or the method semi-name. But if we look inside its prototype, we can see them. It turns out that the prototype of objects created by a class is a reference to the object stored in the property prototype of that class. Remember that when you use a function constructor to build an object, the prototype of that object is set to the prototype property of the function constructor. Well, it's the same for classes. When you define a class, you can think that it will create a function of the name of that class, which will have the same body as the constructor of the class. Then it will create the property prototype and assign it an object. It will add a property constructor pointing to banana. And it will add all the methods, getters, and setters of the class. So when we create a banana object, it will have own properties defined in the constructor, and will have access to methods, getters, and setters by finding them in its prototype chain. This behavior allows several objects to share the same methods. When you compare it to objects created with object initializers, methods, getters, and setters are own properties. And that's not the only difference. When defining a class, they are non-enumerable, while they are enumerable when defined with object initializers. Let's now talk about class fields. Class fields are writable, enumerable, and configurable properties of the object being created. They are also called instance fields. To create them, you just need to give them a name in the body of the class. You can assign them a value, like you would do with a variable, but if you don't, it will be undefined. When you create a new object, these fields will become properties of the object and are not shared between objects of the same type. You can use them like regular properties. Instance fields are added to the instance at construction time, before the constructor body runs, which means that you can use them in the constructor or in any method. You can also use instance fields to initialize all the instance fields, because the value of this, in this context, is a reference to the object being created. One more thing, when it comes to methods and instance fields names, you can use computed expressions like we can with object literals. Classes can create instance fields and methods, but classes can also define a different type of fields and methods called static. To define static fields or methods, we only need to add the keyword static in front of them. What makes static methods and properties different from instance ones is the way we call them and the place they are stored. If we create a new object of the class static stuff, we can see that it doesn't have any properties or methods. And if we try to use them with the instance, we get an error. That's because instead of being stored in the instance like instance fields, they are stored on the class itself. Notice that like instance fields, static fields are writable, enumerable, and configurable, while static methods, like instance methods, are not enumerable. Because they are properties of the class, they can be accessed by using the name of the class. A fairly new feature of class called static initialization blocks enables more flexible initialization of static properties. For example, if you want to store an array in a static field and add values inside that array, we can use a static initialization block like this. Inside the static initialization block, the keyword this refers to the class itself. Before moving on to the next topic, I want to take a bit of time here to talk about the keyword this. The value of this depends on the mode and the context. Classes are always in strict mode, meaning that the value of this can be null or undefined. Inside classes, we have two types of context, the static context and the instance context. As we just saw with static initialization blocks, inside static methods and static fields, the value of this refers to the class itself. Instance context refers to constructors, instance field, and methods. Inside the constructor and instance field initializers, the value of this always refers to the object being created. In methods, this refers to the object that the method was accessed on. It is not always the object created. When it comes to methods, instance or static, we can lose the value of this if, for example, we copy it or pass it to a function. Consider the following example of a class with an instance method losing this, logging the value of an instance property, and a similar static method and static field. If we create an object and give the method as a parameter to set timeout, the value printed is undefined, because here only the function is passed. So when the function is called, no object is found, and this is undefined. We have the same problem with static methods. We can solve this problem by storing arrow functions into fields instead of using methods. Arrow functions don't have their own binding to this, which means that when they are evaluated, arrow functions don't create a new binding to this. Its value retains the value of its surrounding scope. It creates a closure, meaning that the value of this is set to what it was when the function was created, and it never changes. That's the important part. Unlike methods, arrow functions capture the value of this when it's created. We can use that as our advantage. If we redefine our previous class using fields, storing arrow functions instead of methods, we can pass them around, and the value of this stays the same. Let's move on to an important concept of object programming, inheritance. Inheritance is a way for a class to extend another class. That's why JavaScript uses the keyword extends to create a class that is a child of another class. The syntax is very similar to the syntax used by Java. Let's see how it works with an example. Let's say we are a company called Close AI. We develop large language models able to answer any textual questions. We want to provide an API to let developers use our models in their applications. So we define a class called LLM for Large Language Model, with the constructor taking as a parameter the base model. The constructor will call a method loadModel that will fetch the model and store its name in a property. To let users know the existing models, we add static methods they can use without having to create an instance. Let's add a default value to the base model and add an instance field, for example, an alignment parameter that we would use in the constructor to restrict what the model can say or not. Let's add the method answer to answer any prompt. Now we have a full class to use our large language model. We can create an object that loads one of our model. As a reminder, our object contains the instance fields we defined. The instance methods load, model, and answer are in its prototype, while the static method is a property of the class itself. Now we decide to develop a multimodal model, able not only to answer questions, but also to analyze images. Let's create a class and call it LLVM for Large Language and Visual Model, and we make it extend the LLM class. Before adding anything to it, let's try to see what happens when we create an LLVM instance. We get two logs, one telling us that LLM4 is loaded, the other telling us about the alignment parameter. If we go back to the definition of the class LLM, we see that these logs come from the constructor. When we create an LLVM object, the constructor of the class LLM, that is extends, is called. The constructor takes the default value and calls the method loadModel, which prints loadLLM. And then the constructor prints the value of the alignment parameter. The constructor of the parent class is used to create the object. It means that we can use the same parameters. As an example, we can decide to use the model LM3 instead of the default one, and it works. We can see that LLM3 was chosen. Because LLVM extends LLM, we have access to all the methods and fields of LLM. We also have access to static methods and properties. Let's take a closer look at the object LLVM. So it's an object of type LLVM. It has two properties, alignment param and model, and it has a prototype. If you remember what we said previously, the prototype of an object created with the class is the property prototype of that class. So the prototype of the object LLVM is LLVM.prototype. What's interesting here is that the console tells us that this object is an instance of LLM. We can verify that with the keyword instance of. The documentation tells us that the instance of operator tests to see if the prototype property of a constructor appears anywhere in the prototype chain of an object. So instance of is telling us that LLM.prototype is part of the prototype chain of LLVM.prototype. In fact, we don't have to look very far. LLM.prototype is the prototype of LLVM.prototype. Let's recap what we learned with the diagram. So the base class LLM has one static method called existingModels, and it has a prototype property, which is a reference to an object containing the instance methods of LLM, and a constructor property referencing LLM. Then we created the empty class LLVM, which has a prototype property referencing an object, which has a constructor property pointing to LLVM. We also noticed that its internal prototype is a reference to LLM.prototype. So when we created the object LLVM, the constructor of LLM created the properties alignment, param, and model, and its prototype was set to a reference to LLVM.prototype. This mechanism of prototypes is what allows us to use methods and properties defined in the base class LLM. Now, if you look at this diagram more carefully, it doesn't explain how we are able to use the static method existingModels of LLM with LLVM. We are missing a link. As we just saw, inheritance is implemented using the prototype chain. Because the class LLVM is an object, it also has an internal prototype. Let's look at what it is. It's the class LLM. The internal prototype of LLVM is LLM. This is why LLVM is able to use LLM's static properties. You can remember that when using classes and extends, two types of inheritance are happening, regular and static inheritance. We learned that under the hood, classes uses the prototype chain mechanism to use inheritance. Let's go back to our large language and visual model class definition. For now, it's empty. It turns out that at Close AI, we are not very good at making image recognition models. So we decide to use an external model and load it side by side with our language model. To do that, we are going to override the method loadModel of LLM. Overriding happens when you use the same function signature, the same function name and parameters, in the child class. When we create an object of a child class and called an overridden method, the method of the parent class will be ignored and the method of the child will be used. In the loadModel method, we are going to load our visual model, and then we will replicate the behavior of loadModel of LLM. So what's going to happen when we create an LLVM object is that the constructor of LLM will be called, and it will call the loadModel method of LLVM, and then continue its execution. We can verify this behavior in the console by constating the presence of logs load visual model, load LLM, and alignment param. But we did something dirty. Here, we shamelessly copy-pasted the content of the loadModel method of LLM instead of using it. But how can we access it from LLVM? If we take a look at the prototype chain, we see that the method defined in LLVM is added to the object LLVM.prototype, and that we can use LLM.prototype to access its loadModel. But if you've been carefully paying attention, you should realize that it's not going to work properly. compare it to the object previously created. We can see that we are missing the property model in the newly created object. The reason why this is happening is because whenever you call a method, the value of this inside this method is whatever is before the dot of the method call. So we now find a property model on the object llm.prototype. To solve this problem, we can use the call method that any function has. To use it, first write the name of the function or method, then write the method call. As the first argument, give it the value you want this to be inside the method you are using call on. In this case, we want the object being created to be the value of this inside load model. Inside LLVM, the object being created is referenced by this. Finally, we can follow this value with the argument to give to load model. Let's try it out. So now it works. We find the model property inside the newly created object. It works, but it's kind of a workaround. The introduction of method and class also introduced the keyword super. Super gives us the ability to access the parent class, also called the superclass. We can use it for two different purposes: to access properties of the superclass, either by using square brackets followed by an expression, or by using the dot notation. We can also use super as a function call to call the constructor of the superclass. If we go back to our example, here we are trying to call the method loadModel of the class LLM, which is the superclass. So instead of using llm.prototype.loadModel.call, we can use super.loadModel. We can try it out and see that it works properly. While making this video, I got interested in how super really works. So I want to spend a bit of time explaining what's happening, but you can skip this part of the video if you want. If we go back to the evaluation of the super keyword, when accessing a property using the dot notation, we see that it calls make super property reference with the property key and with the current value of this. It also takes the mode it's in. Make super property reference will get the super base. Get super base will get the home object of the function object, which is the method we are calling super on, and store it inside home. Finally, it returns the prototype of the home object. Make super property reference will get the prototype of the home object and store it inside base value, and will return a reference record. In short, a reference record is an internal data structure that is used to track how a variable or property should be resolved at runtime. So here, make super property reference tells us that to find the property with the name property key, we need to look inside the object base value, which contains the prototype of the home object of the function object using super. Confused? Let's see what happens when super.loadModel is evaluated. Make super property reference is called. When called in the constructor, the value of this is set to the object being constructed. The property key is loadModel, and because we are in a class, strict is set to true. With this information, make super property reference will return the prototype of the home object of the function object. Here, the function object is the method loadModel. We are saying that loadModel has an internal property called HomeObject. But what is it, and where does it come from? When you define a method, at one point the operation make method will create the internal property HomeObject and set it to an object. Note that this operation is what differentiates methods from other functions. The value of that object is set during the evaluation of the class, and it takes different values depending on whether it's a static method or not. I will spare you the details and tell you what these objects are. Inside a derived class, which extends a base class, both instance and static methods have an internal slot HomeObject. For instance methods, it's the prototype property of the class, while for static methods, it's the class itself. So if we go back to our example, the home object of the method loadModel is llvm.prototype. Finally, we take its internal prototype. If we take a look at the prototype chain, llvm.prototype's internal prototype is llm.prototype. So you can think that super will be replaced by llm.prototype. If it was a static method, HomeObject would be llvm and its prototype is llm. But why do we care about all this? It has a few consequences. First, because super relies on the internal HomeObject, it only works in methods. Because, as we saw previously, setting HomeObject is what makes a function a method. So if you use super in a method, it works. But if you use a function property, it will not work. Second, unlike this, unbinding or rebinding a method doesn't change the reference of super in it. Before moving on, let's talk about what you can and cannot do with super. If you try to set a property on super, such as super.prop, super will look for the property prop on s.prototype, but will not find it, and instead will set it to the value of this. In this context, this will have the value of the instance d, so d will have the property prop. Next, you can't delete a super property with delete super.prop. Super is a keyword which is evaluated at runtime. It's not a variable holding a reference to an object. You can't read it. You can use super during field initialization. You can use a super static field or method to initialize a static field. You can use a super instance method to initialize an instance field. But you can't use a super instance or static field to initialize an instance field. Okay, let's move on. Let's go back to our definition of LLVM. We can give it the ability to see and answer questions on an image. Now we decide to introduce the ability to browse the internet. To do that, we will create a new class that inherits from LLVM. We call it LLVIM. The first thing that we want to do when creating an LLVIM is to install the web browser plugin. So that's what we do in the constructor. Let's try it out. And we get an error telling us that we must call the super constructor in a derived class before accessing this or returning from the derived constructor. So super is not letting us move on. When you define a class, the engine creates a function object from the constructor and set the property constructor kind to base. But when you extend a class, it will set constructor kind to derived. When you create an object with new, the constructor will use its internal method construct. If we take a closer look at what construct does, it checks the value of constructor kind, and if it's a base constructor, if it is not defined in a subclass, it will create an object. Otherwise, if it's derived, well, it will not create any object at all. And that's why we get this error. When we create a new LLVIM object, it will see that its constructor is a derived constructor, and as a consequence, will not create a new object. JavaScript expects the parent class to create a new object. So whenever we override the constructor, we need to call the parent's constructor using super. Now it works. Remember the field alignment param that we define in LLM? We can override it. Because we are searching the internet, we want to make sure to get safe for work results. So we set the alignment param to SFW. However, overridden fields have a different behavior than overridden methods when they are used in the parent constructor. As we see, the log still shows the value of alignment param as defined in LLM. And that's because of the field initialization order. If you remember, I told you that fields are initialized before the execution of the body of the constructor. And that's why you can use them in the constructor. That was imprecise. In a derived constructor, the call to super is executed first. Then instance fields are initialized. And finally, the rest of the body of the constructor is executed. If you think about it, it makes total sense. Because before calling super, there is no instance to initialize fields on. After the call to super, we will have access to the correct value. We can try showing it with a log. Before the call to super, the alignment parameter has the value restricted, and after, it has the value safe for work. Now that our model can browse the internet, let's override its answer method to first search the internet. Here, we call the LLM's answer method thanks to super. Not that you can use super inside any methods, not only overridden ones. Our LLM classes served us well. But let's give them their deserved rest. We spent quite some time looking at inheritance, how regular inheritance and static inheritance work under the hood, how to override methods and fields, how to use super, but we are not done yet. First, extends is more powerful than it appears. What follows extends doesn't have to be a class. It can be null. In that case, the class prototype will be Function.prototype, and myClass.prototype's prototype will be null. However, you will have to explicitly create and return an object in the constructor. What follows extends can be any expression that evaluates to a constructor function. So you can use a function or a class. You can even do something like this. As a note, JavaScript doesn't support multiple inheritance. An object can only have one prototype, but you can simulate multiple inheritance by merging objects together in a mixin. Built-in classes like array, map, set, and others are extendable, but it is recommended to extend them using classes. We'll see why. Let's say we want to create a special type of array that automatically sorts its element in ascending order. Let's call it sorted array and make it extends array. When we construct a sorted array, we call the array constructor with the elements of the array and we sort it. Let's override the push method to keep the array sorted when we add new elements. Let's see if it works by creating a new sorted array object and pushing elements to it. That was easy, right? Let's see how we would do it with a function constructor. First, we will need to create an array, push its elements, and sort it. Then we will need to set sortedArray2.prototype to an object inherited from array. Then we will need to define the push function on sortedArray2.prototype, and we would need to manually set the constructor property and the prototype. Finally, we will need to return the array. We can see that it's much longer and more complicated than with the class syntax. And if we are not careful, we can easily forget to set the constructor property of sortedArray2.prototype. In most cases, that's not a problem, but the constructor property is used by built-in classes. Methods like filter, map, or slice returns objects by creating them using the constructor property. The consequence isn't obvious at first, but let's see what happens when we don't add the constructor property. If we create an object, push it new elements, everything is fine. Now, if we use map to add 1 to every element, it will create a new array. But if we push a new element to it, the element will be added at the end and the array will not be sorted. That's because when map will create a new object, it will not find the constructor property inside sortedArray2.prototype, but find it in its prototype, which is array. So here, map creates a regular array. If we do the same thing with our object created with the class sortedArray, map creates a sorted array. And if we add a new element, the array stays sorted. Even though forgetting to set the constructor property is most likely a bug, controlling the type returned by a method like map can be a feature. And JavaScript gives us this feature thanks to symbols. As I told you in my previous video, property keys can either be strings or symbols. But I shamelessly didn't show you any examples. Symbols represent unique identifiers. And JavaScript provides a set of symbols that serve as extension points of specification algorithms. In our case, the one we care about is species. Its value is a constructor function that is used to create derived objects. So if we want our sorted array class to return regular arrays instead of sorted arrays, we can modify the value of species by overriding its accessor. Symbols are expressions, so we need to use square brackets. Symbol.species is a static accessor, and here we decide to return the array constructor. So now, if we create a new sorted array, map will create a regular array. Just so you know, many implementers consider the use of species to be one of the greatest mistakes for the language, and they even made a proposal to remove it. One last interesting fact about built-in classes is that there's no static inheritance between built-in classes. For example, because the internal prototype of array.prototype is object.prototype, we would expect array's internal prototype to be object, but it's not. Its prototype is function.prototype. Now that you know inheritance in JavaScript, use it at your own risk. Let's now look at a useful and fundamental idea of object-oriented programming: encapsulation. Encapsulation refers to the practice of bundling data and behavior together within a class or object, and restricting access to that data from outside, creating a sort of black box where internal details are hidden while a public interface is provided to use it in an easier way. Programming languages like Java or C++ implement encapsulation using visibility levels. Each unit, like classes, properties and methods can have one of the three possible values of visibility. Public, which makes them accessible from anywhere. Protected, which make them accessible from within the class and its subclasses, and private, which make them accessible only from within the class. JavaScript, however, doesn't support protected properties. And by default, everything is public. With object literals or function constructors, you can achieve private visibility by using closures. But classes introduce a syntax to make fields and methods private. I will be using the Firefox console instead of the Chrome console for now. Because to better facilitate debugging, the Chrome DevTools supports using and modifying private class members, which make private properties seems like they are public. To make a field or method private, you only need to add a hash before its name. The hash isn't part of the name. Consider it like an operator. You can't read or write a private field, and you can't call a private method outside the class. You can't create a private field or method named Constructor. But you can make private static fields and methods, and you can also create private getters and setters. You can access private fields inside private and public methods using the dot notation. However, you can't use the square bracket notation because the expression will evaluate to a string containing the hash. But the hash is not part of the name of the private field. It is just there to indicate that it is private. You can't use a private field or method without using this. You can call private methods in private or public methods. You can't create a private field in the methods, or you will get an error. It first needs to be declared in the class. You can use private static fields and methods inside other private or public, static or not, fields and methods. Inside static methods, you can access private static properties using this followed by a hash and the name of the private property. This is not recommended because it can create unexpected behaviors with inheritance. Instead, prefer prefixing the private static property with the name of the class. It will avoid problems and it makes it consistent with how you use it in instance methods. It's the same for calling private static methods. Use the name of the class in front of it. According to the specification, private fields are stored in a private map associated with the instance of the class, but separated from it. This has the consequence that private and public names don't conflict with each other. It means that you can reuse the name of a public field for a private one. Let's see an example where this could be useful. Consider a car. The car is moving at a certain speed, but you don't have the ability to directly set the speed of the car, so we should make it private. You can accelerate using the gas pedal or decelerate using the brakes. But when you drive, it's good to know how fast you are going. So we can add a getter to get the value of the private property speed. And because public and private names don't conflict, we can use the same name. Before talking about how private properties work with inheritance, let's add a private method accelerate. Now let's create a supercar class inheriting from car. When you create a supercar object, private fields from the base class will be created and added to the object, which means that you can use the inherited public methods that act on private fields. But that's about it. Private properties are only accessible from within the class they are defined in. They are not inherited by subclasses. If you try to directly access a private property of the parent class, you will get an error. One more thing. Inside a class, you can check the existence of a private property with the in operator. Okay, we've learned a lot of things about classes today. If you want a quick way to remember everything we learned today and more, check out my mind map by following the link in the description. Good job for sitting through this long video. I wasn't expecting it to be this long, but you made it. There are still a lot of details you can learn about objects and classes, but I think I covered the most important concepts. If you would like me to cover any specific topic, let me know in the comments. You can now put your computer back where it belongs and go outside to touch some grass. But before, don't forget to subscribe, like the video, and follow me on Twitter, so I can show my non-existent friends how cool I am. And maybe you can become my friend. This was Computer Bread. Peace. I'm done, finally over. Oh my god, oh, it feels so nice. Finally over.